Okay, so I'm just gonna keep pumping these out. I hope I'd like to anyway, as much as I can. So let's continue talking about potential energy, and I'm gonna beat a dead horse here, but I really need you guys to get this. Potential energy can only come from a conservative force, which means that your energy that you put in is available to get back out, okay? That potential energy that you put in, you're going to get back out regardless of the path that you took. All you have to do is lower the object in gravitational force, and the object moves with a spring in along the x direction. Say if it's sliding back and forth in the x direction, it only needs to move in that direction, and there will be potential energy either stored or given back. Okay, that's great. For non-conservative forces, those are path dependent and lose energy from the system all along the way. So no matter what happens, you're losing energy from these non-conservative forces. Friction is the best example of it. And it's non-conservative, path dependent, stripping away mechanical energy and turning it into heat. Heat is just photons, okay, of light in the infrared part of the spectrum. So when you feel something is hot, you're feeling the photons hitting your hand. You're not seeing the photons, you're feeling them. And it's just infrared part of the spectrum. That energy is wasted. It's gone. There's nothing you can do about that. So it's hard to get back, in other words, to make it useful to do something. Okay, so let's, I just wanted to do that before we started talking about an example. I can talk about the exact differentials before the example or after. And so I think I'm going to talk about it after and show you the examples so we can talk a little bit about conservative versus non-conservative forces. So let's do it. This is in the book. It's example 8.5. And this is how you can check and see if you have conservative or non-conservative force, okay? A way to check. Conservative versus non-con. Okay, all right. So, let's just talk about it a little bit. If, let's say, we've got f dot dr, okay? Two vectors dot each other. If that is a quote-unquote exact differential, and we'll get to what that is in a minute, then the force is conservative. then the force F is conservative. Okay. So we're going to do an example. It's the best way to do it. All right. Before we do, what it boils down to is dfx dy is equal to dfy dx. If that's true, this must be true to be a conservative force. Okay, and that is equation 8.10. But let's just go into our example real quick instead. So we have a force. We're given this force. It's 5 newtons per meter in the y times y in the I hat direction, plus 10 newtons per meter times x in the j hat direction. Okay, so far so good. We all know that f dot dr is going to be equal to f of x. You know what? Let's talk about this for a second. F dot dr. First of all, what is f? We've just laid out what f is. F of x in the I hat direction plus f of y in the j hat direction. Of course, if there was a z, we'd add that too, but there isn't. Okay, what is dr? Dr is equal to dx I hat plus dy j hat. And then, of course, if there was a k direction, we'd do the dz in the k hat direction. Okay, so f dot dr then is going to give us f of x dx plus f of y dy. What is f of x? F of x is equal to 5 newtons per meter times y. F of y is equal to 10 newtons per meter times x. Let's leave that one there at the top. Okay, now what do we need to know? We want to know this guy. Let's circle it. We want to know these things. Okay, so what do? We're going to take the derivative of f of y with respect to x, and that's going to be 10 newtons per meter. We're going to do the derivative of f of x with respect to y, and that happens to be 5 newtons per meter. And if you notice, those are not equal to each other, right? So that does not equal 5 newtons per meter. Okay. So this force is not exact differential. Okay. All right. So let's talk about exact differentials, and let's learn a little bit about what the heck is going on here, because the world wants to know. So du, we already let's zoom back out. Come on. Okay, sorry about that. We already talked about how U is our potential energy, and that equals minus our work done by the force. We said that. That implies that du is equal to minus d work. And that d work is equal to our minus our force times our whatever our displacement d length is, whatever random direction we're going to go, dx, y, z, whatever. So if it happens to be that the force is in line with dl, then it's just the FL component in the dl direction. And that's what you get. Okay, so we can take this one and equate it with this one. So we have du equals minus FL dl. And then that will give us that du dl equals, we'll put the minus sign here, f of l. Okay. So that means in general, I want to just reiterate that L is random direction. But let's not talk randomly. Let's talk about something specifically. We've got F. Let's say that it's all in the x direction. And what does that happen to equal? Well, that happens to equal minus du dx in the I hat direction. Okay, another way to do that is to add directions. So we can do the same thing, but we can have it with x and y, which is what we need. So we're going to add y, and that equals minus the partial of u with respect to x, I hat plus, I said plus, but what I really mean is negative, minus the partial of u with respect to y in the j hat direction. All right, so far so good. So what were we doing earlier? We were taking the derivative with respect to y of du dx. And let's just make that negative. Okay. Because that equals the derivative of f of x with respect to y. And then we also did, which we want to be equal to. So the question is, are these things equal? df of y dx, which happens to equal, for sure, d dx du dy. Okay, so do you guys get where we're going here? This guy, this guy, and this guy should be equal. The order of differentiation shouldn't matter. So I'm going to just write them down as positive here. And the question is, are they equal? Because you should be able to just swap these guys. It doesn't matter the order. They should work, right? So technically, we should be able to say that if we swap those two, dx, dy. So the order in which we do the operation, the derivatives, does the order matter? Okay. So if the order doesn't matter, then of course this is equal to that, right? Because we're saying the order doesn't matter, and we have just switched these guys, right? Just switch them around. In this situation, the order doesn't matter. That's a conservative force. The order of derivatives that you take. So if the order of derivatives doesn't matter, then it is a conservative force. Okay, and that's this situation we just proved that they shouldn't really matter technically, algebraically, not calculus-wise, but algebraically. However, they might not necessarily be the same. And if the order of derivatives matters, then the force is non-conservative. Okay. And in that case, then we don't have a question anymore about it. We get that those things are not equal. Okay, so that is the that's the notion of exact differentials. We've already talked about our we've already talked about a lot of the roller coaster, right? I think we've killed the roller coaster, but I want to talk about. Well, I just want to make sure that we have killed it. I think we did. I think you guys get it. What if what if we do a couple of things? Oh gosh, I think my fever is kicking back in. Okay, what if we put a couple of things in on our I apologize. Let's go back to let's come back here to our graph of the roller coaster. I'm going to clean this up a little bit right here. We're going to put a point here. That's 0.7. And we can zoom in, I guess. Let's do that. Okay, so here's 0.7, and then let's say here's 0.6. And instead of having a force of friction that is 125. In fact, I don't even know if I want to use 500. I did this in my notes, and I want to add in what that force of friction is. Okay, so 1120 newtons is now our force of friction. I don't know if you guys saw me write that, but it's right here. Okay, so we have now increased our force of friction to 1120, and we're kind of done with all of, we're done with this. You'd think it would erase faster the region. But it doesn't. It's interesting, right? I certainly don't want to clear the screen. Okay, so my question is, are we going to make it to 0.7 if our friction is up here? If our friction is this, are we going to make it to this 0.7? So 0.6, what is the height? 3 meters. 3 meters. 0.7, I don't know. It's also D is equal to 60 meters. What is the kinetic energy at 6, and what is the velocity at 6? Okay, so we want to know what our kinetic energy at 6 is. That's a question, not a equals. So these are the questions. Let's find out. We're going to write down the equation first. So our E total mechanical, and you guys know that the total mechanical energy is going to drop off because it's not the energy total, which is energy total, which I just wrote, minus the work of the non-conservative force at 6, i.e. friction. And let's figure out what the work of the non-conservative force is. That's the work of friction at 6. And that's 1120 newtons times our 60 meters. And that's 67200, 67200 joules. We've got our total at 2,500, 122,500, 122.5K minus 67.2K in joules. So that's our total energy, total mechanical at 6. And that is, what is it? 55,300 joules. Okay, now we can solve for, we can solve for the, we need a little more room here. Okay. We can solve for our kinetic energy because our energy total mechanical is equal to our kinetic energy plus U. We're doing it all at 0.6. So what is a U of 6? That's 3 meters high. 3 meters, U of 6. So that's MGH6, which is, we've got our 500 kilogram cart, 9.8 meters times 3 meters. U of 6 is equal to 14,700 joules. Okay, so we can plug U of 6 in here, and we can solve, since we know this one, we can solve that for the kinetic energy at 0.6 equals our energy total mechanical at 6 minus our U at 6, our potential energy at 6. 55.3 kilojoules minus 14.7 kilojoules gives us a KE of 40,000. 40.6 kilojoules. Now we need to figure out what that, so there's one thing. What does that equate to in velocity? Our V6 is equal to the 2 times kinetic energy over our mass square root. And that ends up, I'm not going to walk you through all the numbers. I've got it right here. It's 12.7 meters per second. Okay, so that's V6. All right, so since we still have a velocity here at 0.6, we're climbing the hill. We still have a velocity. The question is, are we going to make it? Well, will we make it to the top? Will we make it to 0.7? Where the heck are we going to get to? We don't know. We have no idea. But let's find out. So, I'm going to write these down. KE at 6 is equal to 40.6 kilojoules. U at 6 is equal to 14.7 kilojoules. And V6 is equal to 12.7 meters per second. Now I can erase all of this stuff. It doesn't erase as fast as the board, the whiteboard at school. What do I expect for free software? Okay. Will it get to 0.5? Well, that's all the way up here. This is 0.5 right here. So will it get there? I don't know. It has to go another 7 meters high. So the difference, H, 6 to 5, is equal to 7 meters. So it has to get up another 7 meters. Well, let's find out, what is 7 meters? What is the potential energy of 7 meters? And so U6 to 5 is equal to mgh 6 to 5, and that's 500 times 9.8 times 7 meters. U6 to 5 is 34.3 kilojoules. Kinetic energy at 6 has to be greater than that. And our kinetic energy at 0.6 is right here. And looky there, it's greater. So we might just make it. So the kinetic energy at 6 is greater than the potential difference between 6 and 5. So we might make it. Okay. All right. Let's find out though. Let's find out. Get a little bit more space here. Okay. All right, will we make it? I don't know. What is the work of friction from 6 to 5? Right? We want to know from 6 to 5 how much friction energy are we going to lose? So that's 60 meters to 80 meters. 60 meters to 80 meters. So our new frictional force is 1120 newtons. And we're going an additional 20 meters. And that equals 22.4 kilojoules. So we've got this 22.4 kilojoules. If we add 22.4 22.4, I was just making sure, kilojoules, plus our potential difference of 34.3, that's this. That's how much potential energy we have to put into the system to get up that high. If we add those things together, we end up with 56.7 kilojoules. So 56.7 kilojoules, but we only have this right here. We only have 40.6 kilojoules in kinetic energy. So we are not going to make it. Our KE at 6 is less than 56.7 kilojoules. And because of that, we don't make it. Up to 0.5. Okay, so we've got 0.7, And I'm going to just put in a little bit of stuff here. At 0.7, our height is equal to 9 meters. And our distance is equal to 70 meters. So here's 0.7. So we're not going to make it from 0.6 to 0.5. Okay, so that's out of the question. But what is still a part and could still happen is we're going to end up getting somewhere in there. Okay, we're going to get in there, somewhere in there, between 6 and 5. I'm gonna go back here, and you guys remember the picture, but let's look at it. Let's look at it in a way like this. And let's say this is 0.6 and this is 0.7 and here's 0.4. Okay. This is our potential energy diagram. So we can, oh my gosh, that did not work. In fact, I don't like any of this. So this is our potential energy diagram. Here's the absolute bottom. That's 0.4. We've got a 0.6 and we've got a 0.7. And let's not even worry about what 0.7 is actually. Let's forget about the numbers assigned to it. We do know that 0.6 was 3 meters high above zero. And it was 60 meters along the track. Okay, that's good. 0.7 we don't care about. We do care that it's our turnaround point, okay? So essentially, we have enough energy to get up to that point and then turn around. All right? So if the car stops and reverses direction, it will gradually come to a stop at the bottom. So let's use blue. So here we come swinging through. Okay, everything's going great. We get up to this turnaround point and we stop. And then we come back. And then we're going to go like this. And then we'll stop. And then we'll come back. And then we'll go like this. And we'll stop. And then we'll come back. And then we'll go like this. And we'll stop somewhere. Let's say here. And we probably won't stop exactly at 0.4. In fact, it's pretty much guaranteed that you won't stop at the very bottom because friction. Friction doesn't allow gravity to do its thing completely either, okay? It wants to suck the energy out of the system and drive it to equilibrium as fast as possible. So this would be our equilibrium. So a non-conservative force, well, let's not do that. Let's just say friction drives a system to equilibrium. Okay, so, and it would never actually end up being exactly at 0.4. Okay. Now, let's find out. I have a question. All of this raises a question to me. What minimum angle? So this is an angle at this point. This is an angle. So that's theta 7. This is theta 6. What is the minimum angle? Where the force of gravity overcomes the frictional force. So yeah, we want to know what that angle is. So what do? We go back to the things that we know so well. And we say, okay, here's our thing. Here's our force of friction. Here's our normal force. Here's our mg. This is our mg cosine of theta. There's our mg sine theta. We're going to be to the point where the force of friction balances with the mg sine theta. So in the x direction, if we consider this to be x and this is y, in the x direction, our sum of the forces x is equal to 0. Right at that point, mg sine theta is positive, minus f of force of friction is negative, guaranteeing that the force of friction is equal to mg sine theta. We end up with theta equals the arc sine of our force of friction divided by mg. So what is that? Well, we've got two. We can say we had our first force of friction was what, 125? Let's use 125. I don't want to look. 125 newtons. But we also had 1120. Okay, newtons. So we're going to have a theta for each. Okay, there's theta 1, here's theta 2 for each one. Theta 1 is going to equal the arc sine of 125 over 5. Wait, it's not 500. It's closer to 5,000. It's 4,900 newtons. Okay, so theta 1 is equal to 1.45 degrees. Theta 2, that, my friend, is 13.2 degrees. And we're gonna say that is patently has to be less than this angle. So our theta has to be less than theta 2 for so it could stop. Here's the point. Let's draw the thing again. Here's our point. There's the bottom. And let's say that's 13.2 degrees. So at this point, we're at 13.2 degrees. And down here at this point, we're at 1.5 degrees. So here, between here and here, if our frictional force was 125 newtons. I'm falling apart, guys. Hold on, just bear with me 1 second. We're almost done. 125 newtons. Okay, 125 newtons. This is the range that it would stop in if we had the 1120 newtons. It could end up anywhere between there and there. The lower the friction, the closer you will stop to 0. Okay, so if you had 0 friction, eventually, or very small friction, because if you had 0 friction, it wouldn't stop there at all, unless it couldn't get out of the well. It might end up in that position. But if it has no friction, of course, it will never stop. It would roll back and forth forever. If it has just a tiny, tiny bit of friction, the smaller the amount of friction, the closer it will end up to this very bottom point. Okay? So that is I think that kills this lecture. For now, we're going to come back and talk about stability in a little bit. Thank you.